Welcome everyone.
Question number 141. For the continuous beam shown in the figure 12.60, the influence line diagram for support reaction at D is best represented as continuous beam A, B, D, and at point C there is an internal hinge into the beam. Total length of the beam is 2L. Span AB equal to L and span BD equal to L, but BC is equal to L by 2 and CD is equal to L by 2. Now considering the vertical reaction, the free body diagram of the continuous beam will be like this: vertical reaction at A, vertical reaction at B, and vertical reaction at D. And we have to find out the influence line diagram for this support reaction at D. Let's assume an unit load acting at a distance x from the support D, and as there is an internal hinge at point C, so summation of all the moment at point C is equal to 0. Okay, for this right part, so we can write RD means reaction at support D, RD into this distance L by 2, triangle rotated in anti-clockwise direction, and the opposite moment will be this unit load into L by 2 minus x, triangle rotated in clockwise direction. So these two moments are opposite to each other, so we can write RD into L by 2 equal to 1 into L by 2 minus x, and after simplification RD will be equal to 1 minus 2x by L. We got the equation RD equal to 1 minus 2x by L. So as per this equation, the value of RD will change. At point D, the value of x equal to 0, so RD value will be equal to 1 unit, so 1 unit is drawn here. And when the value of x is equal to L by 2 at this point C, the value of RD will be equal to 0. So we can clearly connect these 2 points at the end of 1 unit, and at point C we can connect the straight line, and then we will get the influence line diagram for the support reaction at D.
Option C is right answer.
142. Figure 12.62 shows a portal frame with one end fixed and other end hinged. The ratio of the fixed end moment MBA by MCD due to side sway will be. So this is portal frame A, B, C, D. Frame is fixed at point A and is hinged at the point D. Length of CD is equal to L by 2 and the moment of inertia 0.5 I, and length of AB is equal to L and moment of inertia is I. As the portal frame is subjected to horizontal loading P at point B, so sway moment at B will be 6 EI del by L square.
And del is the deflection caused by the horizontal loading at B and C.
And for the vertical member CD, whose length is L by 2 and moment of inertia is equal to 0.5 I, the sway moment at point C will be 3 EI del by L square, because the end C is fixed but end D is hinged. Now moment MBA equal to 6 EI del by L square, but moment at C MCD will be equal to 3 E I is equal to 0.5 I into del divided by L square, that means 0.5 L square. After calculation, MCD will be equal to 6 EI del by L square. Now if we make the ratio MBA by MCD, the ratio will be 1. Option A is right answer. Number 143. Figure 12.63 shows a portal frame with loads. The bending moment diagram for this frame will be. So a portal frame is given in the question. Okay, the load is uniformly distributed. Load is given on the top chord or top member. Now see, the frame is hinged at both ends. So at this hinge support there will be horizontal reaction, and at this hinge support there will be also horizontal reaction. So for this horizontal reaction from this support there will be some moment at this point, force into distance. So there will be some moment at here but 0 at here, because there is no moment for hinge connection, so 0 at this point. As there is horizontal reaction at this hinge support, so there will be some moment at this point. So moment at here is 0, but there will be some moment under the horizontal reaction, that is at here. Now see the top chord or top member where UDL load is acting. There will be two bending moment opposite to each other. One is free bending moment, that is simply supported moment, free moment, and another is fixed end moment. Okay, so fixed end moment will be at both the ends, at this end and at this end, and this value will be equal to WL square by 12. And the free moment, that will be at the midpoint of the top member, and the value will be equal to WL square by 8. Free moment diagram will be parabolic in shape, and at these two fixed end there will be some fixed end moment. So fixed end moment at this end is WL square by 12, and at this end WL square by 12. So rectangular shape fixed end moment diagram will be available for the top chord member. Now superimposed bending moment diagram from this two bending moment diagram is our actual bending moment diagram for this portal frame.
Option D is right answer. Question number 144. Figure 12.65 shows a Pratt truss. The influence line for force in member BC will be.
So for this Pratt truss, we have to determine the influence line diagram for the force in the member BC, the vertical member BC. Okay. Now see, when the unit load at A, D, E and F, the force in the member BC is equal to 0. Okay, but when the unit load at point C, the force in the member BC is equal to 1. Okay, so we can easily draw the influence line diagram for the force in the member BC. So when unit load at C, the force in the member BC is equal to 1 unit, and 0 at A and 0 at D for this panel.
Option C is right answer. Question number 145. A two-hinged semicircular arch of radius capital R carries a concentrated load W at the crown. The horizontal thrust is.
For two-hinge semicircular arch of radius R, when it carries a concentrated load of W at the crown, the horizontal thrust value will be W by pi. But when subjected to uniformly distributed loading W per unit length, the horizontal thrust will be 4/3 WR by pi. And when a parabolic arch is subjected to a concentrated load at the crown, the horizontal thrust at both the end of the arch will be 25 WL by 120 H. And when subjected to uniformly distributed loading of height H and length of the arch is L, and the loading is W per unit length, the horizontal thrust value will be WL square by 8H.
Option B is right answer. Number 146. The rigid portal frame shown in the figure 12.67 will not have any side sway if where I1 is the moment of inertia of the column cross section, I2 is the moment of inertia of the beam cross section. So the portal frame will have no sway if the loading is symmetrical about the center line. Option C is right answer. Question number 147. For the portal frame shown in the figure 12.68, the shear equation is.
Portal frame A, B, C, D is given, fixed at both the support at A and D, and we have to find out the shear equation for this portal frame. The shear equation is the summation of all the forces in horizontal direction is equal to 0. Does not matter its sign. Okay, either it is leftwards or rightwards. Irrespective of the sign, the summation of all the horizontal force is equal to 0. So from this support we will get a horizontal direction HA, and from this support we will get a horizontal direction HD, and here at point B horizontal loading P is there. So we can write the shear equation HA plus HD plus P equal to 0. Now we will determine the value of HA and HD. Okay, and then we will put the value of them in this equation number 1. Then we will get the final shear equation. Okay, so for this vertical member AB, okay, there will be moment generated at this fixed support, okay, A, and at this fixed support B. These two moments will be of same nature. The horizontal reaction HA will create a moment which will counteract them. Summation of moment at point B equal to 0. So we can get HA into 4, which is equal to MAB, the moment at point A, plus moment at B, MBA. Now after calculation, HA will be equal to MAB plus MBA by 4, And similarly for the vertical member CD, we can find out HD. HD value will be equal to MCD plus MDC divided by 4.
By taking moment at point C.
Now the value of HA and HD in equation, if we put in equation number 1, we will get the final CR equation MAB plus MBA by 4 plus MCD plus MDC by 4 plus P equal to 0.
Option C is right answer. Question number 148. Due to some point load anywhere on a fixed beam, the maximum free bending moment is capital M. The sum of fixed end moment is.
So this is our fixed beam AB, and concentrated load W is somewhere in the beam. Suppose this load is at a distance small a from the capital A and at a distance B from the support capital B. Now fixed end moment at A is equal to WA B square by L square, and fixed end moment at support B is equal to W A square B by L square. And under this loading, the simply supported or free bending moment at this point with the loading will be WAB by L, and that is equal to M as given in the question. Now we have to determine the summation of fixed end moment FEM at A and FEM at B, and the summation of these two moment is equal to what? So MA plus MB will be equal to WA B square by L square plus WA square B by L square. We know A plus B is equal to L, length of the beam, and after simplification we will get the summation of two fixed end moment MA plus MB will be equal to WAB by L square into A plus B, or WAB by L, and that is also equal to capital M given in the as per given in the question.
A is right answer. 149. A steel frame is shown in the figure 12.69, where EI is constant throughout the frame. Joint O of the frame is rigid. The rotational stiffness of the frame at point O is given by.
Now we have to find out the rotational stiffness at joint O, and the joint O of the frame is rigid. So rotational stiffness at the joint O will be OA plus OC plus OB plus OD. Now rotational stiffness when the far end is fixed, then the rotational stiffness value will be 4EI by L, and when the far end is hinged, then the rotational stiffness value will be 3EI by L for a beam, and when the far end is free, then the rotational stiffness value will be 0. So for member OA, near end is O, far end is A, so far end is fixed, that means the rotational stiffness value will be 4EI by L. Now for member OC, the rotational stiffness value will be also 4EI by L. Now for member OB, B is hinged, the far end is hinged, so the rotational stiffness value for member OB will be 3EI by L. And for member OD, the rotational stiffness value is 0 because the far end is free. Now if we calculate all the value by summing all the value, then the rotational stiffness at the joint O will be 11EI by L.
Number 150. Consider the following statements in the beam shown in the figure 12.70 for all positions of load W except x equal to 0. Statement 1. The bending moment is maximum at B. Statement 2. Bending moment is maximum under the load. Statement 3. Deflection is 0 at A. Statement 4. Deflection is 0 at B. So this is a propped cantilever beam, okay, subjected to a concentrated load W at a distance x from the support B. Support B is fixed supported end, and support B is fixed supported end, and support A is simply supported end. So for simply supported end, moment at the end is 0, but deflection is also 0, but rotation is not 0, okay. But for the fixed supported end, deflection and rotation is 0, but there exists some movement into the supports, and the maximum bending moment will occur at the fixed end support B, and it is greater than the moment formed at the point where concentrated load exists. Option D is right answer. Question number 151. A fixed beam of uniform cross section is carrying a point load at its midspan. If the moment of inertia of the middle half length is now reduced to half its previous value, then the fixed end moment will increase. Option A is right answer.
A higher EI means the beam is stiff and it can resist the deflection more effectively. So fixed end moments will increase.
Question number 152. The maximum bending moment at the left quarter point of a simple beam due to crossing of UDL of length shorter than the span in the direction left to right would occur after the load had just crossed the section by. So this is our simply supported beam AB, and total length of the beam say A, and as per question at the left quarter point, that means at point C, maximum bending moment occurs. Okay, and let's say length of the load, that is UDL load shorter than the span, is equal to B. Now we know maximum bending moment at any section occurs when the section divides the load in the same ratio as it divides the span.
In this special case,
So we can easily calculate span ratio of the beam, left part divided by right part, and if we do that, the span ratio will be 1/3. Now we can easily calculate the length of load to the left of the section or left part of the point C is equal to 1/1 plus 3 into the total load B, which will be equal to B/4, and the load to the right of the section, that is point C, will be 3/3 plus 1 into the total load length B, that will be equal to 3B/4. So we can clearly say the load had just crossed the section by 3/4 of its length. Question number 153. When a load crosses a through type truss in the direction left to right, the nature of force in any diagonal member in the left half of the span would. This is our truss. When the load is at F, the force in the member CG will be the compressive in nature, and when the load is at G, the force in the member CG will be tensile in nature. Option A is right answer, change from compression to tension. Question number 154. In the figure 12.71, X, Y and Z are the deflections under A, B and C due to loads P and Q. X dash, Y dash and Z dash are the deflections under A, B and C due to unit load at point C. The deflection Z would equal, in first case, this is a simply supported beam. Okay, so deflection at A is equal to X, and at B is equal to Y, and at C is equal to Z under the load P and Q. These are the two concentrated vertical load. And now in second case, the deflection at point A is X dash, and at B is equal to Y dash, and at C is equal to Z dash under the only concentrated load of 1 unit at point C. Now by Maxwell's reciprocal theorem, consider these two diagram. Under these two diagram, del AB equal to del BA. So the unit load acting at point A with deformation delta at point B is equal to unit load acting at point B with deformation at point A. Okay, now as per this theorem, we can also equate this load into this deflection P into X dash plus this load, vertical load, into this deflection at point B, Y dash, is equal to this load 1 unit, this vertical load in 1 unit into deflection at point C, that is equal to Z. So Px dash plus Qy dash is equal to 1 into Z. Now Z will be equal to Px dash plus Q into Y dash.
option B is right answer.
Question number 155. The influence line RC for the beam shown in the figure 12.72 will be as in
Continuous beam, one end overhang, that is DE, and subjected to internal hinge at point B. Now we have to draw the influence line for the support RC. So this is your baseline from A to E. RC is the support direction at point at support C. Now say unit load 1 unit is acting at a distance X from acting on the beam at a distance X from the support D. Now let's take moment at point D. So summation of all the moments at point D is equal to 0. Now RC is the reaction at support C, so RC into L, equal to unit load 1 into x, that is in opposite direction, so RC will be equal to x by L. Now if we put x is equal to 0, RC will be equal to 0. That means at this point D is equal to 0. X is equal to, when x is equal to L, RC value will be equal to 1 unit. So RC value will be equal to 1 unit. Now if x is equal to 1.5 L, the RC value will be equal to 1.5. Now if x, the value of x is equal to minus L, then the value of RC will be equal to minus 1. Now as RC is equal to 1 unit, as the value of RC is equal to 1 unit, so the value of RA will be equal to 0 unit, and RD is also equal to 0 unit. So if we connect this point and this point, there we will get the complete impedance line diagram for the beam.
Option B is right answer. Question number 156. The moment at the intermediate support of a two-span continuous beam of 6 meter each with simple supports at the ends carrying a UDL of 20 kN per meter over only the left span is where flexural rigidity is same for both the span.
This is our continuous beam A, B and C. The span AB is subjected to a uniformly distributed load 20 kN per meter of length 6 meter. The bending moment diagram under this UDL will be parabolic in nature. Okay, so the center of the parabola from the support A will be equal to 3 meter. 6 by 2 equal to 3 meter, and the area of the bending moment diagram will be 2/3 into base into height. So 2/3 into base is equal to 6 meter into height is equal to WL square by 8, that is equal to 90 meter. So the area will be equal to 360 meter square, and x1 is the distance from the center of CD of the parabolic bending moment diagram from the support A, that is equal to 3 meter. 6 by 2 equal to 3 meter. And to find out the bending moment at point B, that is intermediate point, intermediate support, we have to utilize the three moment equation, that is equal to 2mb into L1 plus L2. L1 is the span AB length and L2 is the span BC length, is equal to 6A1 x1 by L1 plus 6A2 x2 by L2. There will be no A2 x2 because there is no the span BC is not loaded, so there will be no bending moment diagram and no value for second term 6A2 x2 by L2. So only 6A1 x1 by L1 is written here. Now L1 L2 is equal to 6 plus 6 equal to 12 meter. Now we got A1 equal to 360 meter square and x1 is equal to 3 meter and L1 is equal to 6 meter. Putting all the value, MB will be equal to 45 kN meter. That is the intermediate fixed end moment at the intermediate support B.
Option B is right answer. Number 157. For the rigid frame shown in the figure 12.74, the force required for moving the girder AB through a horizontal displacement del is given by.
So this is our rigid frame subjected to a horizontal loading at point A, fixed at this end and hinged at this end. Okay, and subjected to a horizontal loading P at point A, and AB is the rigid girder whose moment of inertia is infinity. That means which will not bend under the loading, under this kind of loading, that is sway loading. Okay, so this is fixed end and this is also fixed end due to rigidity of the girder, but this is hinge end and this is B, this end B is fixed end due to rigidity of the girder. So as the two vertical member, this member and this member will undergo some deformation under this horizontal loading, that is called sway, that is del at here, that we will calculate the stiffness for this vertical member and for this vertical member. So for this vertical member, stiffness will be 12 EI by LQ because this is fixed end and this is also fixed end due to rigidity of the girder, and stiffness of this vertical member will be 3 EI by LQ because this is hinge end and B is rigid end due to rigidity of the girder. Now total force required to produce a displacement of del, that is the sway deflection, is equal to summation of the force resisted by each column. So P will be equal to Q1 plus K2 into delta. we got K1 equal to 12 EI by L cube and K2 equal to 3 EI by L cube. P, now putting the value in this equation, P will be equal to 15 EI del by L cube.
Option D is right answer. Number 158. For the portal frame shown in the figure 12.75, the final end moments are MAB equal to 15 kilonewton meter, MBA equal to 10 kilonewton meter, MCD equal to 20 kilonewton meter. The end moment at MDC will be.
So this is our portal frame ABCD. Length of the member BC is 10 meter, length of member AB and CD is equal to 5 meter. And at the center of the member AB, a horizontal load 10 kilonewton is acting. Now see, as this is a horizontal loading 10 kilonewton, so we will consider only the horizontal reaction at the both support at A and at D. Suppose say horizontal reaction at support A is equal to HA and horizontal reaction at support D is equal to HD. Now taking moment at point B, so summation of moment at point B is equal to 0. If we take moment HA into 5 in clockwise direction minus this fixed end moment MAB and MBA minus this load 10 into 2.5 equal to 0. MAB equal to 15 kilonewton meter and MBA equal to 10 kilonewton meter. As per equilibrium, summation of all the force in horizontal direction is equal to 0. So HA plus HD minus 10 equal to 0, or HA plus HD equal to 10 kilonewton. We got HA equal to 10 kilonewton, so HD will be equal to 0 kilonewton. Now taking moment at point C, HD into 5 minus the fixed end moment at MCD, at C MCD and at D MDC equal to 0, and we got HD equal to 0, so MDC will be equal to minus 20 kilonewton meter.
Option B is right answer. 159. The slope deflection equation at the end B of the member BC for the frame shown in the figure 12.76 will be.
This is our portal frame ABCD. Support A is fixed, support D is also fixed support, and a horizontal loading 100 kilonewton is acting at the point B. Now we have to determine the slope deflection equation at the end B of the member BC of the frame. Okay, so MBC will be equal to fixed end moment at BC plus 2 EI by L into 2 theta B rotation at B plus theta C rotation at C. Fixed end moment at point at BC will be equal to 0, as there is no loading except this horizontal loading which is acting at point B. The moment value at B will be 0 because the only load is acting at point B. So putting all the value in this equation, we will get MBC will be equal to 4 EI by 8 into 2 theta B plus theta C. EI is equal to 2 times 2 EI. L is equal to 8 meter. So 4 EI by 8 into 2 theta B plus theta C.
Option C is right answer. Question number 160. Total degree of indeterminacy, both internal and external, including both internal and external, of the plane frame shown in the figure 12.77 is.
Now for this plane frame, we have to determine the degree of indeterminacy. The formula for ds will be equal to 3m plus r minus 3a minus r. R is the number of release or number of additional equation due to hybrid joints. M is the number of member of the frame. R is the number of reaction by the supports, and J is the number of joints. And R is involved in the equation when the structure is subjected to internal hinge. So under this internal hinge, 4 members are connected. Okay, so the value of R will be equal to 4 minus 1 equal to 3. Now putting and M equal to 12 because 12 number of member is there. 1 2 3 4 5 6 7 8 9 10 11 12. R is the number of reaction by the support. So at this support, this is fixed support, this is fixed support, this is fixed support, and this is fixed support. So 4 number of fixed support are there. For 1 number of fixed support, there are 3 reaction components. One is horizontal reaction component, number 2 is vertical reaction component, and number 3 is fixed end moment component. So 3 at this end, 3 at this end, 3 at this end, and 3 at this end. So total 12 reaction components available from this structure. And R, capital R value is equal to 3, and number of joint is equal to 11. 1 2 3 4 5 6 7 8 9 10 11. Okay, now putting all the value in equation ds equal to 3m plus r minus 3j minus r, we will get ds is equal to 12.
Option C is right answer. Number 161. For the beam shown in the figure 12.78, an influence line diagram is shown in the figure 12.79. This refers to the
Euler Base law principle states that the influence line for any internal force like shear moment is the deflected shape of the structure, which when it is subjected to a unit displacement corresponding to that force. Since the diagram shows a characteristic split on or vertical shift at a specific point along the span, it represents the shear force at the specific section.
See, option D is right answer. Question number 162. Match list 1, and they are beams with list 2 influence line, where influence line for BM given, and select the correct answer using the codes given below the lists.
Option A is the cantilever beam PQ, the influence line for bending moment for this beam will be maximum for the unit load at the fixed end when the load will be at Q, and the bending moment will increase linearly. Okay, and the diagram of the bending moment will be triangular in shape given in option 2, and the ordinate of the triangle will be L. Next, option B. Here simply supported beam is given, and unit load is acting at a distance L by 4 from P, and total length of the beam is L. Now at this point, the value of bending moment or ordinate of the bending moment will be 1 into this length L by 4 into this length 3L by 4 divided by total length of the beam is L. The value will be equal to the 3L by 16 given in option number 1, and the bending moment diagram will be triangular in shape. Next, option C, simply supported beam subjected to a unit load at the midpoint. Okay, so the bending moment diagram will be triangular in shape, and ordinate of the triangle at the middle will be load into the total length of the beam by 4, so L by 4. Now at option D, cantilever beam is given PQ, where unit load is acting at the midpoint, so the maximum bending moment will occur at the fixed end, and the ordinate of the moment value will be L by 2, load into distance L by 2, so ordinate value will be L by 2, and shape of the diagram will be triangular in shape as well. Option A is right answer.
Question number 163. The beam shown in the figure 12.81 carries loads of 20 kN and 40 kN at points X and Y respectively, and produces a deflection of 6 mm at point Z. To produce deflection of 8 mm and 5 mm at X and Y respectively, the load required at Z would be.
In first case, at the simply supported beam AB at point X, the vertical load is 20 kN, and at point Y, the vertical load is 40 kN, and at point Z, the deflection is 6 mm. And in second case of the simply supported beam at point X, the deflection is 8 mm, and at point Y, deflection is 5 mm. But at the point Z, the vertical loading is 5 kN. So from these two scenario of the beam, by Maxwell's reciprocal theorem, we can write this load 20 into this deflection plus this load 40 into deflection 5 mm is equal to this vertical loading P into deflection 6 mm, and after calculation P will be equal to 60 kN.
Option C is right answer. Question number 164. A portal frame is shown in the figure 12.82. For EI constant, the deflected shape of the frame will be.
The frame will undergo sway under the horizontal loading, and the movement will be like in option A.
Option A is right answer.